Hi and welcome back to the STM32 Beginner's Guide series. In this video, I am going to show you how you can generate the PWM signal using your STM32 microcontroller. I will show you how to calculate and set the frequency of the generated PWM signal to any value that you want. I will show you how to calculate the duty cycle and set the duty cycle percentage to any value that you want. And I will also show you how to write code to generate a PWM signal that you can use to control the brightness of an LED. My name is Ali and you are watching CGHQ. What is PWM and what does it do? Pulse Width Modulation, also known as PWM, is a crucial technique which allows digital devices like microcontrollers to generate analog-like values. This is achieved by rapidly switching a digital output between its high and low state at a specific frequency, effectively creating an average analog output value. This technique can be used to deliver power to electronic components like LEDs, motors, or even audio devices. There are two main important things to consider when working with PWM. This is the frequency of the PWM signal and the duty cycle of the PWM signal. The frequency of a PWM signal is the number of times the signal completes one full cycle, covering one high and one low state per second, measured in hertz. The duty cycle is how long the signal is on the on state compared to the off state in one cycle. It is typically expressed as a percentage. This means that if a 50% duty cycle is set on the signal will be on for half of the time and off for the other half. And a 25% duty cycle would mean that the signal is on for a quarter of the time and off for 3/4 of the time. For example, if your PWM signal was alternating between a magnitude of 3.3 volts and 0 volts, if you set the duty cycle to 50%, then the average output analog voltage would be 50% of 3.3 volts, which is 1.65 volts. And if the duty cycle was set to 75%, then the average output analog voltage would be 2.475 volts. So in conclusion, the frequency controls how fast the PWM signal cycles between the on and off state, and the duty cycle controls how long the signal stays on during each cycle, effectively affecting the average output voltage. Let's talk about how PWM is generated using timers in the STM32 microcontroller. Timers in microcontrollers are hardware peripherals that count clock pulses to measure time intervals. They can be used to track the passage of time, to create delays, or to generate specific time-dependent output. How timers work is that they start counting at an initial value. This value is usually 0, and they increment their count based on the input clock signal. This input clock signal can either be from a microcontroller system clock or from an external clock. This counting can be influenced by a prescaler value, which divides the clock signal to make the timer count a bit slower, extending the range of the time intervals it can measure. For example, the STM32F41RE has a maximum system clock of 84 MHz. If you set the prescaler to 83, the timer will count at 1 MHz. This is calculated as the system clock divided by 1 plus the prescaler value. So it would be 84 MHz divided by 84, which gives us 1 MHz. Once the timer reaches its maximum value, which is often 255 or 2 to the exponent of 8 for 8-bit timers, it overflows and either resets back to 0 or triggers an interrupt to signal that the maximum count has been reached. This maximum count value can also be set to a different number by the counter period. And I'll show you how to do that as we continue with this series. When timers are used to generate PWM, they can operate in different modes, like the fast PWM mode or the phase correct PWM mode. The first PWM mode is the one I've been talking about, where the timer counts up to a maximum value before it resets back to 0 or triggers an event. Then the phase correct PWM mode is when the timer counts up and then counts down to create a symmetrical PWM signal, which is much more stable. Okay, now let's talk about configuring a timer for PWM generation using your STM32 microcontroller. So we can start with the PWM frequency calculation. If you want to set the frequency of your generated PWM signal, the equation that you would use would be the clock frequency that you supply to your timers. This can be your microcontroller system clock, or it can be an external clock. So you take that clock frequency and you divide it by 1 plus the prescaler value that you choose. multiply by 1 plus the counter period needed to set the PWM frequency value to a value that you want. So in this example, we will be setting the frequency of our PWM signal to 20 kilohertz. So in order to achieve this, we can say 20 kilohertz is equals to 84 megahertz, which is the maximum frequency that we can get from the STM32 F41RE. And then we're going to divide this by 1 plus a prescaler. A prescaler, you can choose any value that you want. However, there's a limit on which value you can use depending on the type of microcontroller that you have. In this example, I'm just going to use 19 as our prescaler value. So it's going to be 1 plus 19 multiplied by the counter period. Since we have one unknown in this equation, we can make the counter period the subject of the formula to see which value we would need to achieve the desired PWM frequency. After doing these calculations, we see that to get a 20 kilohertz PWM frequency value for a microcontroller with a clock frequency of 84 megahertz, the counter period value that we would need is 210 minus 1, which is 209, because we start counting from 0. To calculate the duty cycle for your generated PWM signal, there's a specific value that you need to add to the compare register. And to determine what this value should be, you basically take your desired duty cycle value divided by 100, since it's a percentage, and you multiply by the previously calculated counter period value. So for example, if we want a 75% duty cycle, this would be 75% of 210. 210 being the counter period value that we calculated on the previous slide. So it would be 75 over 100 multiplied by 210, which is 157.5. So this value can also be rounded up to 158 when you're actually implementing this into your code. So if you want a 50% duty cycle, that would be 50% of 210, which is 105. And if you want a 25% duty cycle, that would be 25% of 210, which is 52.5. Again, if you are coding this, you can just run the value up to 53 on your code. Let's start writing code to generate PWM using our STM32 microcontroller. We're going to start by opening STM32 Cube IDE. Then we come here to create a new STM32 project. Then we're going to go to port selector and search for F401RE, because that's the microcontroller we're using in this series. Click on the microcontroller and then click on next. Here in project name, you can just call the project PWM, and then we'll use the default location to save it. Then click on finish. If we move on to the left, we can see here where it says timers. You can use any of these timers for PWM generation, but for this video we're going to use timer 2. And then here for this series, I'm just going to choose to use pin PA5 for our PWM output. So we're just going to left click on the pin and then select the pin as timer 2 channel 1. As you can see, the pin is orange. If it's orange, it means it's not yet fully initialized. So we need to come over here and click on timer 2. And then here at clock source, we need to either choose whether we want to use an external or an internal clock. For this video, we're going to use the microcontroller's internal clock. So just click on internal clock. And then if you look at the pin that we selected, it's timer 2 channel 1. So here where it says channel 1, we need to click and then scroll all the way down and select PWM generation channel 1, because we want to use this timer to generate PWM on the selected GPIO pin. Here, this is where you can configure the settings for your timer and everything that has to do with the PWM generation. But before we can get into that, our microcontroller is rated to operate at clock speeds of up to 84 megahertz. But this does not mean that the microcontroller would always be set up to 84 megahertz straight from the box. So to make sure that it operates at 84 megahertz, you can come to clock configuration, and you can see our microcontroller is currently set to operate at 16 megahertz. So what we're going to do is we're just going to come here and then we're going to write 84 so that our microcontroller operates at its maximum clock speed. After we click enter, it says no solution found using the current selected sources. Do you want to use other sources? You can just click on OK, and it will try multiple different configurations until it finds one that can actually output the required 84 megahertz for our example. So we're just gonna give it a couple of seconds while it's busy searching for a solution. Okay, so now as you can see, our clock speed has been set to 84 megahertz. So now we can just go back to pin configuration and then finish setting up our timer settings for PWM generation. So if you can remember from our previous slides, we established that we need a prescaler value of 19 and we need to set the counter period to a value of 209. So here, this is where you set the prescaler value. So the prescaler value is a 16-bit value. This means that you can set any value between 0 and 2 to the exponent of 16. So we're gonna set ours to 19. Click on enter. And then here on counter mode, this is where we select how our counter should count. Should it count from 0 going upwards, or should it count from the maximum number going downwards? We're just gonna leave it as up. And then this is the counter period. So here we're just gonna type 209 because in the previous slide we determined that to get a desired PWM frequency of 20 kilohertz we need a counter period of 209. So just click on enter. And then some of these don't really matter for now. We're just gonna come here. It says PWM generation channel 1, and then mode is PWM mode 1, and then fast mode disable. I'm just gonna click on enable for now. And then if you look here on the right side, we see that the pin that we selected, PA5, is now green. This means that the pin has been fully initialized for PWM generation. So what we can do is that you can either click Ctrl S to save, or you can come here to file and then click on save. And then we're gonna say yes, we want to generate code, and yes, we want to change perspectives. Okay, so this is the main C file. Let's just take a quick look at what we have already in the code before we start coding. Since we're using timer 2, if you hold on control and click, it shows you where timer 2 has been configured and how exactly timer 2 has been configured. So some of these things here match the ones that we just set on the STM32 Cube MX graphical initialization tool. So for example, if you can see, it shows us here that we're using timer 2 and our prescaler value has been set to 19, and then our counter period has also been set to 209. So it just shows you how the timer has been initialized in code as well. The timer has been initialized, yes, but it hasn't been started. So before we can actually generate PWM, we need to start the timer. To start the timer, we're just gonna type HAL_TIM_PWM, and then you can click on control and space so that you can see the available options to complete this line of code. So what we're going to do is that there's multiple ways to start the timer for PWM. There's the simplest way, which is just starting the timer, and then you can start the timer using DMA. DMA just stands for direct memory access. And then there's another one here that says PWM start_IT. This IT means just stands for interrupt. So we're not going to use direct memory access, and we're not going to use interrupt. Instead, we're just going to use the normal one. So you just double click on this one, and then here just double click on this. Here at the channel, we're going to type TIM_CH, and then we can hold on control and click space for auto completion. And then we're going to use timer 2 channel 1, because remember, if we go back to the IOC, remember that PA5 is linked to timer 2 channel 1. So in our main code, we need to set it to timer 2 channel 1. Okay, so now that we have started our timer, we need to come here to this infinite while loop. So in this infinite while loop, this is where we're going to set the duty cycle of our PWM signal. So we're gonna come here where it says user code begin 3. So we're just gonna write _HAL_TIM_set_compare, and then we can just hold on control, click space for auto completion. So we see that we need to state the timer that we're using, the channel that we're using, and the value for the compare register. Remember that the value that we want to load onto the compare register is the value that's going to set the duty cycle of our PWM signal as calculated on the previous slide. So what we're going to add here, we're just going to take this line of code here, copy, and then paste it here. Take this one as well, timer_channel 1. Paste it here as well, and then now we need to determine the value that we need to set our duty cycle. For a 50% duty cycle, we need to load a value of 105 into the compare register. Remember that this value directly corresponds with this 210, which is the value that we calculated to achieve a frequency of 20 kilohertz. So if you go back to our code, we're just gonna type 105 and then put a semicolon. This is for 50% duty cycle. When this is done, we can basically just upload the code to our microcontroller and then try to see if we can measure the generated PWM signal. So I'm just gonna come here and click on build, which is this icon with a hammer, and then you can see it says build finish with 0 errors and 0 warnings. What we're gonna do now is that we're gonna take our microcontroller and connect it to our computer using a USB cable. We're gonna come here to this green play button that says run, click on it, and then go to the debugger, and we can actually just click on OK. When this is done, it says download verified successfully, shutting down and exit. This means that our code was successfully uploaded into our microcontroller. To see the generated PWM signal, we're just gonna hook up an oscilloscope to the pin that we selected to output the signal, which is pin PA5. As you can see on the oscilloscope, we do have a generated PWM signal, and if you look closer, we can see that the duty cycle is at 50%, which is the value that we set in our code, and the generated frequency is the 20 kilohertz that we calculated as well and set using a prescaler value of 19 and a counter period value of 209. Now we can write the code to automatically adjust the brightness of the LED. So I'm just gonna cut this line of code here, and then I'm gonna create a for loop that will automatically increase and decrease the brightness of our LED by varying the duty cycle. I'm just gonna say for int I is equals to 0, semicolon I less than 210, which is the maximum value for our duty cycle, another semicolon I plus plus, so that the duty cycle can increment by 1 each time this loop starts from the beginning. And then inside, I'm gonna paste that the code we just removed to set the value inside of the compare register. And then instead of sending 105, we're just gonna send the value contained within the I variable. And then before we can exit this loop, I'm just gonna add a small delay. So I'm gonna say HAL underscore delay, hold control, click space, double click, and create a delay of 2 milliseconds. Then I'm just gonna copy this for loop and paste it below so that we can create a secondary for loop that will decrement the duty cycle when it reaches its maximum value. So I'm gonna say int I 210, and then we're gonna say greater than 0, and we're gonna say, instead of plus plus, we're gonna say minus minus. And then when this is done, we're just gonna click on the run button and upload the code to the microcontroller. Okay, errors exist in the okay, it seems like we have a slight error in the code. Oh yes, we forgot a semicolon next to the delay, this delay as well. So just click on run, upload the code to the microcontroller, and then we see it finished building with 0 errors and 0 warnings. Okay, so now that the code has been uploaded, we can hook up the LED to the microcontroller and see how the PWM signal is controlling the brightness. We can also hook this up to the oscilloscope so that we can see the duty cycle changing. In this episode, we've learned about PWM, we've learned about how we can configure timers and how to calculate the necessary values to achieve a specific PWM frequency and duty cycle. We also learned how we can control the brightness of an LED using the generated PWM signal. In the next episode, we will take this further by learning about analog to digital conversion, otherwise known as ADC, where we will read ADC values from a potentiometer and use the values to control the brightness of an LED. Thank you so much for watching. If you found this video helpful, please like, share, and subscribe. And if you have any questions, please leave them in the comment section below. Thank you.